Moving on to 13.10 potentiometer. Potential difference is usually measured by an instrument called a voltmeter. The voltmeter is connected across the 2 points in a circuit between which potential difference is to be measured. It is necessary that the resistance of the voltmeter be large compared to the circuit resistance across which the voltmeter is connected. Otherwise, an appreciable current will flow through the voltmeter, which will alter the circuit current and the potential difference to be measured. Thus, the voltmeter can read the correct potential difference only when it does not draw any current from the circuit across which it is connected. An ideal voltmeter would have infinite resistance. However, there are some measuring instruments such as digital voltmeter and cathode ray oscilloscope which practically do not draw any current from the circuit because of their large resistance and are thus very accurate potential measuring instruments. But these instruments are very expensive and are difficult to use. A very simple instrument which can measure and compare potential differences accurately is a potentiometer. A potentiometer consists of a resistor R in the form of wire on which a terminal C can slide. The resistance between A and C can be varied from 0 to R. As the sliding contact C is moved from A to B, if a battery of EMF E is connected across R, the current flowing through it is I is equals to E upon R. And if we represent the resistance between A and C by small r, the potential drop between these points will be Ri is equals to Re upon capital R. Thus, as C is moved from A to B, small r varies from 0 to R. And the potential drop between A and C changes from 0 to E. Such an arrangement, also known as potential divider, can be used to measure the unknown EMF of a source by using the circuit shown in figure 13.25. Here R is in the form of a straight wire of uniform area of cross section. A source of potential cell whose EMF Ex is to be measured is connected between A and the sliding contact C through a galvanometer G. It should be noted that the positive terminal of E and that of the potential divider are connected to the same point A. If in the loop AGCA the potential C and the negative terminal of Ex are at the same potential, then the two terminals of the galvanometer will be at the same potential and no current will flow through the galvanometer. Therefore, to measure the potential Ex, the potential of C is so adjusted that the galvanometer shows no deflection, and under this condition the EMF Ex of the cell is equal to the potential difference between A and C, whose values ER upon capital R is known, and in case of wire of uniform cross section, the resistance is proportional to the length of the wire. Therefore, the unknown EMF is also given by Ex is equals to E R upon capital R, or E is equals to small l upon capital L, where capital L is the total length of the wire AB and small l is its length from A to C. And after C has been adjusted for no deflection, as the maximum potential that can be obtained between A and C is E, so the unknown EMF Ex should not exceed this value. Otherwise, the null condition will not be obtained, and it can be seen that the unknown EMF Ex is determined when no current is drawn from it, and therefore potentiometer is one of the most accurate methods for measuring potential. The methods for measuring the EMF of a cell as described above can be used to compare the EMFs E1 and E2 of two cells. The balancing lengths L1 and L2 are found separately for the two cells. So E1 is equals to E L1 upon L and E2 is equals to E L2 upon L. And dividing these two equations, we get E1 is equals to L1 E1 upon E2 is equals to L1 upon L2, and so the ratio of the EMFs is equal to the ratio of the balancing lengths.